Welcome to the materials for the fifth session in this mass spectrometry course, and in this session we're going to continue looking at quadrupoles and particularly ion traps. In this part of the course we're looking at the quadrupole based mass analyzers, so that's the quadrupole mass filter, the 3D ion traps and the linear ion traps. And in the last session we started off by looking at the quadrupole mass filter. We began by looking at the shapes and arrangements of the electrodes required to produce quadrupolar electric fields. Then we went on to look at the two main modes of operation of linear quadrupoles. That's the mass filter mode, where you can produce mass spectra, and the RF only mode, which you can use to guide ions with no mass selection. And then we looked at the voltages applied to the quadrupole rods and the electric fields that they produce. In this session, we're going to begin moving on from the linear quadrupole to the quadrupole ion trap, also known as the quadrupole ion store, or Quistor, the 3D ion trap, or the Paul trap, after its co-inventor, the Nobel laureate Wolfgang Paul. The other co-inventor named in the patent is Helmut Steinvedel. In fact, Paul and Steinvedel are the fathers of the entire quadrupole mass spectrometry field. If you click here, you can jump to their original patent. You can see the ion trap design is shown in figures 11 and 12 amongst a variety of other quadrupole-based mass analyzers that they also described. As we discussed in the previous session, to make the 3D ion trap shape, you take the 2D quadrupole configuration and rotate it around its central axis. This results in a 3-electrode structure, 2 end caps, and a central electrode called the ring. As with the linear quadrupole, if we apply the right voltages to these electrodes, we can trap ions in the center and use them to perform mass spectrometry. The voltages used for ion traps are very similar to those used for quadrupoles. They're of the form U plus V cos omega t, whereas before U is a DC offset, V is the amplitude of a radio frequency alternating potential, omega is the frequency of that potential, and T is time. But unlike the quadrupole mass filter, for ion traps the voltage is only supplied to one of the electrodes. In most commercial systems, the end caps are kept at ground, and the alternating potential is only supplied to the ring electrode. In preparation for this session, you were asked to read through Ray March's tutorial introduction to ion traps and write out in your own words the derivation of equations from 2 to 24. If you haven't done it already, I recommend pausing this session now, undertaking that first, and then coming back. In the workshop, I'll get you to talk through your experiences from following this derivation. As you'll have seen in the Ray March tutorial, the Mathieu equations for 3D ion traps are similar to those for linear quadrupoles, but they're not identical. The multiplying coefficients on the top of both the A and Q equations is twice what it was in the normal quadrupole mass filter equations, and the denominators include both an R0 squared term and a Z0 squared term, whereas the normal quadrupole equations only included the R0 squared term. Additionally, the stable region in the stability diagram isn't the same shape in ion traps either. It's now a sort of elongated quadrilateral shape. And we'll go on to look at the stability diagram in more detail a little later in this session. The key feature about quadrupole ion traps is in the name. They trap ions. Unlike in a linear quadrupole where the ions just pass through the length of the quadrupole, trapped in the X and Y direction by the quadrupole fields but free to move in the Z direction down the length, in a 3D ion trap, the ions are trapped within a confined region, and while they're there, there's a number of different things we can do to them. We can selectively get rid of some of the ions out of the trap by boundary or resonance ejection, and we'll cover those terms later, but these are essentially what allows us to isolate ions of a particular mass in the trap, or eject ions out mass sequentially so we can build up a mass spectrum. We can also excite ions by putting energy into them by manipulating the way they move in the ion trap, and this allows us to deliberately break the ions into parts. And because these different modes of operation happen on a population of ions trapped in a single place, we can put them together in different orders to undertake different experiments. And so if we have an external ion source creating ions, we can trap those ions in the ion trap, we can ramp the RF to selectively eject them one mass after another, and so we can create a mass spectrum. Or if we want to do something more advanced, we can trap the ions coming from an ion source, we can resonantly eject all the ions except for one that we're particularly interested in, so we can isolate an ion, we can then excite that ion and cause it to fragment, and then we can generate a mass spectrum of the fragment ions. And so the 3D ion trap is the first mass analyzer we've looked at that's capable of undertaking tandem mass spectrometry. It can select a parent ion, fragment it, and generate a mass spectrum of the product ions. So let's consider the constraints and capabilities of ion traps. And first we'll start with the pressure. In both time-of-flight and linear quadrupole analyzers, we needed a pretty good vacuum because we didn't want the ion to collide with background gas molecules as it progressed through the instrument. But in ion traps, we actually need some background gas in the trap. When you're trapping ions in an ion trap, low-energy collisions with a background gas cool the ion, they reduce some of its kinetic energy and so make it easier to trap and makes the ions collect in the centre of the potential well. And when you're trying to get ions to fragment in ion traps, we do that usually by collision with background gas molecules at higher energy, so again you need gas in the trap then. So as a general rule, the vacuum needed for ion traps to work is going to be of the order of 10 to the minus 3 to 10 to the minus 4 millibars, which compares to 10 to the minus 6 for quadrupoles, and maybe 10 to the minus 7 or better even for TOFs. Next, let's consider the speed. Just like quadrupole mass filters, quadrupole ion traps generate mass spectra using an RF ramp process. However, unlike quadrupoles, they also need to have trapped their entire population of ions beforehand, so the time taken for a mass spectrum includes both the ion trapping time and the time taken to do the RF ramp. And that means that in practice, ion trap mass analyzers are fairly slow. For weak ion signals, you may need to trap ions for a long time, maybe 500 milliseconds, so then at most you're going to get something of the order of 2 mass spectra per second. If the incoming ion signal is stronger, for example from a more concentrated sample, you may be able to reduce that ion trapping time. And then you may be able to reach rates of something like 10 mass spectra per second. However, this slow rate of mass spectral analysis means that ion trap instruments are not generally suited to very fast front-end separation techniques like fast GC. Ion trap instruments also tend to have fairly modest resolving power, something of the order of a few thousand, maybe 5,000 to 10,000 in a very good instrument. This means that you'll be relying on the front-end chromatography and the fragments produced by tandem mass spectrometry if you need to identify molecules in ion traps. The poor mass accuracy that we see in ion traps isn't solely a result of the low resolving power, it's also caused by an effect called space charge that we'll cover later in this session. And we'll have a complete session dedicated to tandem mass spectrometry later in the course. And this brings us on to tandem mass spec in this list. So unlike the time of flight and quadrupole mass analyzers, a single ion trap is capable of tandem mass spectrometry. It can trap ions, isolate a single one, fragment that, and collect a mass spectrum of the product ions in a single analyzer. Regarding sensitivity, ion trap instruments have a pretty good sensitivity, and this is due to 2 main reasons. Firstly, they use the same kind of multiplying detectors that both the time of flights and the quadrupole mass filters used. And secondly, ion traps have the capability to change the length of time that they accumulate ions for before they collect a mass spectrum. So if the ion signal is particularly weak, an ion trap can increase the length of time it accumulates ions for before it collects a mass spectrum, and so boost the sensitivity. But if the ion accumulation time remained long when the signal was strong, this could result in overfilling the ion trap with ions or overloading the detector. So most ion trap instruments can dynamically change the ion accumulation time during, say, an LC or GC run in order to optimize the number of ions in the trap at a given time. And this capability is usually called automatic gain control, or AGC. Next, I'll handle cost and complexity at the same time, because they're related. Single ion trap mass spectrometers are relatively low cost, pretty simple instruments, at least on a mass spec scale of things. A top-end mass spectrometer may contain over 10 mass analyzer or related components, and it could cost £1 million or more. Whereas a relatively simple single ion trap mass spectrometer may be less than £100,000. So it's cheap on a mass spec scale of things, but it's not something you'd go out and buy 5 of on a Friday night. The last thing we'll look at for ion traps is the mass range. As with quadrupole mass filters, in quadrupole ion traps, the higher the mass you want to look at, the higher the voltages, both the DC offset and the RF amplitude, that you have to apply. So the mass range in these instruments tends to be limited by how much voltage you can put on the ring electrode before you risk arcing onto the end caps, which would damage the instrument. So as a general ballpark estimate for the upper mass to charge range for ion trap instruments, it's of the order of 10,000. So far in these quadrupole sessions, we've looked at 2 different types of mass analyzer: the linear quadrupole and the ion trap. And next I want to combine those 2 ideas together into the third class of mass analyzer, the linear ion trap. A linear ion trap is constructed like a quadrupole split into 3 sections. And linear ion traps are sometimes known by their initials as LITs, or also sometimes as 2D ion traps. Linear ion traps are called 2D ion traps because the quadrupolar field only traps the ions in 2 dimensions, in the quadrupolar plane. So this is in the X and the Y directions. The quadrupolar field isn't what's trapping the ion in the Z direction, that's down the axis of the quadrupole. In order to trap ions in this Z direction, the center section of the linear ion trap is held at a lower potential than the 2 end sections. In the absence of a background gas, the incoming kinetic energy of the ions would cause it to pass straight through this and out the other side. But because there's background gas in a linear ion trap, the ions lose some kinetic energy and get trapped in this potential well. And once the ions are trapped in the center section, then we can use the quadrupolar fields to manipulate them. So as with a 3D ion trap, we can isolate ions, we can cause them to get excited and fragment, and we can generate mass spectra of original ions or fragment ions. The difference between the linear ion trap and the quadrupole ion trap is that for the linear ion trap, we use the standard quadrupole equations, because in 2 dimensions it's just the same as a linear quadrupole, whereas in the 3D ion trap we have to use the quadrupole ion trap equations, as we went through in the Ray March tutorial. So given that a linear ion trap offers the same modes of operation as a quadrupole ion trap, ion trapping, mass scanning, isolation and fragmentation, what's the benefit of a linear ion trap? The benefit is that in a quadrupole ion trap, all 3 dimensions of the trapping volume are defined as a function of the quadrupole radius. But in a linear ion trap, only the X and Y dimensions are limited by the quadrupole radius. The length can be made arbitrarily long. So that means that in a linear ion trap we can have a much larger internal volume, and that gives linear ion traps what's called a larger space charge capacity. The concept of space charge is very important for people using ion trap instruments. In an ion trap, you're trapping a fairly large number of ions in a relatively confined space. So if we're working with positive mode mass spectrometry, we have a large number of positive ions compressed into a relatively small space. But all these positive ions are positive ions, so electrically they repel one another. Effectively, the electric fields in the ion trap are trying to push the ions together, and the electric field created by the ion cloud itself is trying to push the ions apart. The more ions you try to put in an ion trap, the stronger the repulsive force from all those ions being packed in together, So effectively an ion trap has a volume that you can fill up with ions. You simply can't put more ions in without the new ions pushing old ions out. Or to put it another way, the more ions you put into the ion cloud, the stronger the electric field of the ion cloud, which is counteracting the electric field you're trying to impose on it from the mass spectrometer. Now remember that the motion of the ions in the quadrupole is a function of the voltages that you apply. Remember the U and V terms in the quadrupole equations. As you approach the space charge capacity of the trap, the electric field of the ion cloud is changing the voltages that the ions in that cloud see, and that has the effect of changing the A and Q parameters of the ions. And this means that the space charge affects the mass accuracy of ion trap instruments. This space charge capacity can also have an effect on the quantification capability of mass spectrometers. And it's for this reason that ion trap-based instruments tend not to be used for those experiments where quantification is of prime importance. But the intensity of the space charge effect depends on how small a volume you're trying to compress your ion cloud into. And because linear ion trap instruments have a much larger internal volume for the same quadrupole radius than 3D ion trap instruments, linear ion traps are much less affected by space charge than their 3D alternatives. And it's for this reason that the vast majority of ion trap instruments sold these days are linear ion traps rather than 3D ion traps. So apart from the greater space charge volume which gives linear ion traps greater dynamic range, they broadly have the same constraints and capabilities as 3D ion traps. So the same pressures, speeds, resolving powers, capacity for tandem mass spectrometry, sensitivity, complexity and cost are broadly identical. Now we're going to spend some time looking at ion motion within quadrupoles, the frequencies that ions move at, and some resonance effects. If we want to understand how ions move inside mass spectrometers, one of the easiest ways to do this would be if we could see the ion beam. But the ion beam is made up of tiny particles inside a metal vacuum chamber, usually, so how can you visualize this? Well, ion beams have been visualized in the past. So for example here, this group put a metal plate at the end of a quadrupole, and after leaving the quadrupole running for a long period of time, they were able to image the shape of the ion beam exiting the other end. Another way to image ion beams is to put some kind of scintillator, that's like an old phosphorescent TV screen that lights up when charged ions hit it, and that way you can take images of what the ion beam looks like, in this case what happens to an ion beam when it passes through this grid of holes. But these techniques have their drawbacks. Firstly, you've got to build a special system with a special detector in it. And this is extremely expensive and quite time-consuming. And although these can show you what the ion beam looks like at particular places in the instrument, for example as it exits the mass analyzer, what they can't show you is exactly how the ions got to that point. And even worse, what if you build your mass spectrometer, put one of these detectors in, and then find that the ion beam doesn't go where you want it to go? Well, what do you do then? Are you going to build a completely new instrument? There's got to be a better way, surely. Well, luckily, there is. There's a kind of software you can get called an ion trajectory modelling package, and this is specifically designed for these kind of problems. In this kind of software, you build virtual mass spectrometers inside a computer. The software then works out the electric or magnetic fields that will be associated with that design of instrument, and then flies ions through to see how they'll behave under those conditions. So if you want to build a new design of mass spectrometer, the first thing companies will do is build a virtual version inside one of these modelling packages, fly ion beams through it and check to see what the performance would be in a real instrument. Then based on the results of these tests, they may have to make changes to the design in the computer, and they can keep iterating that design until they get the performance they want, before they actually have to go on and build anything. One of the most common ion modelling packages is called Simian, and here you can see it being used to model a quadrupole. But many other packages exist. So for example, another alternative is IT-Sim that came out of the Cooks Group in the US, and it's mainly designed for modelling ion traps. So using this ion trajectory modelling software, you can really look at how ions move through mass analyzers. And you can model any kind of mass analyzer, so time of flight, ICR, orbitraps, or in our case particularly quadrupoles. Over on the right here, I'm showing the trajectory of a particular ion passing along the length of a quadrupole under specific conditions. Of course, in this view, we're looking at the ion trajectory in terms only of its x and y positions. But in Ion Modelling Package, it's easy to turn the quadrupole on its side and see how the ion flies along the length. So let's do that. So now you can watch the path that the ion takes as it travels down the length of a quadrupole from an ion source towards the detector. And if you watch closely, you can see that the path the ion takes isn't a simple sine wave. Also, if you look on this side, you can see that the motion in the x direction isn't the same as the motion in the y direction. Because this ion motion is being generated in computer software, I can simply record the position of the ions as a function of time. So for that ion you saw flying on the previous screen, here I've recorded its position in x and y as a function of time separately. And I was able to set the model up specifically so that the a and q coordinates of the ion were q equals 0.7 and a equals 0.15. And looking again at the ion trajectory, now it should be even more clear that the ion motion is not a simple sine wave either in the x or the y direction. In both cases, these are complex motions that contain more than one frequency, and as it happens, what those frequencies are is really important. If you want to know what the frequencies are in some oscillating signal, then there's a special mathematical tool known as the Fourier transform that can tell you. The Fourier transform concept is a really important one for analytical chemists to understand, in particular because it's the basis of instruments like Fourier transform infrared, NMR spectroscopy, and a complete class of mass spectrometers, the Fourier transform mass spectrometers. So because of this, I really strongly recommend following the YouTube link that I've provided on this slide. This will take you to the 3 blue, 1 brown graphical explanation of how the Fourier transform works. And it is by far the most easy to understand and intuitive explanation that I've ever seen for this. So, I hear you gibber with barely constrained excitement. What happens if you Fourier transform the ion trajectories to reveal the underlying frequency components? Ah well, your wish is my command. Here it is. And what this shows us is that both the x and the y motion contain multiple different frequency components, and that they're different in each case. Just to declutter the graph, let's concentrate only on the frequencies in the x direction. You can see that the ion motion is made up of several frequencies. We call the lowest frequency the fundamental, and the higher frequencies the higher order components or the harmonics. Now one thing to note is I'm not showing the ion frequency in absolute terms, as in the ion frequency in terms of hertz or megahertz. I'm showing the ion frequency relative to the quadrupole drive frequency. So that means if the ion was moving with a frequency that was exactly the same as the quadrupole drive frequency, it would have a relative frequency of 1. Whereas if it was moving with half the drive frequency, it would have a relative frequency of 0.5. So let's see what the frequencies of the various components in the ion motion were. So the fundamental frequency is 0.163 times the drive frequency, and the next harmonic is 0.837, then 1.163, 1.837, 2.163, and I already know the next one is going to be 2.837, and so on. You've probably spotted that there's a pattern in those numbers, but we'll come back to that in a minute. First of all, let's look at the relative intensities of the different harmonics. You can see that the fundamental has the highest peak, meaning it's the largest component of the motion, and that's normal. And then the other higher harmonics have lower intensities, and the higher frequency you get to, the lower the intensity of that harmonic. So now let's come back and look at the pattern in the components of frequency in the ion motion. Although this range of frequencies might look complicated, in fact you can create them with just 2 formulae. So in these formulae, little omega is the ion frequency, capital omega is the quadrupole drive frequency, n is an integer starting at 0 and going up, and beta is a factor that allows us to relate the quadrupole drive frequency to the ion frequency. Now n equals 0 corresponds to the fundamental frequency, so we'll start with that one. So we have little omega 0 minus equals 0 minus beta upon 2 big omega, and little omega 0 plus equals 0 plus beta upon 2 omega. And if we tidy up the zeros in those equations, they end up looking like this. And because the frequencies correspond to cosine waves, a positive frequency is the same as a negative frequency, so that means minus beta upon 2 omega is the same frequency as plus beta upon 2 omega. So both these frequencies are the same, and so we can just write them like this. So that means we'd expect the fundamental frequency to equal beta upon 2 times omega. Or, to rearrange that equation in a different way, we can say we expect the ion fundamental frequency divided by the quadrupole drive frequency, and that's the relative frequency, to equal beta upon 2. And conveniently, it's the relative ion oscillation frequency that we're already showing in this spectrum. So as we know what the relative fundamental frequency is, now we can solve for beta. And now we know what beta is, we can calculate all the other harmonic frequencies. So we'll expect to find a pair of frequencies at 1 minus beta upon 2 and 1 plus beta upon 2. And sure enough, in the spectrum we can see the peak at 0.837 and 1.163. And then for n is 2, we expect to find another pair of frequencies at 2 minus beta upon 2 and 2 plus beta upon 2. And those are the two peaks at 1.837 and 2.163. And then there'll be another pair of peaks for n is 3, n is 4, n is 5, but with ever lower relative intensities. And in this case we've gone through the process of calculating beta and then all the higher order harmonics for the motion in the x direction. And we could repeat that process for the same ion's motion in the y direction and calculate the beta for that. And the trajectory from which we derived these frequency components came from an ion with a particular a and q coordinate. So what happens to the ion frequencies and therefore the beta values for ions with different a and q coordinates? So in order to demonstrate the frequency effects of changing the a and q coordinates of ions, I've calculated the ion trajectories all the way along the base of the stability diagram. So for all the results you're about to see, a equaled 0 and q is scanning from 0 to almost 1. So at each value of q, I've Fourier transformed the ion trajectory to reveal the component frequencies, and that's what I'm displaying here, where the x-axis, remember, is the ion frequency divided by the drive frequency, so it's the relative ion frequency. The current value of q is shown here. And there are several peaks in the frequency spectrum, but the lowest frequency is the ion fundamental, and that's omega 0. And the next peak up is the first harmonic. As you can see, as q increases, the frequency of the ion fundamental also increases. But at the same time, the frequency of the first harmonic is decreasing, and its relative intensity is increasing. As we keep increasing q, these two frequencies move closer and closer towards each other, and they'll meet at a relative frequency of 0.5. So you can see the ion fundamental frequency and the first harmonic merged at a q value of 0.908. And actually, if you look further up in the frequency spectrum, you can see the second and third harmonics merged at the same value of q. Now remember, from this relationship we knew that the relative fundamental frequency equaled beta upon 2. So all we had to do to solve for beta was to find the peak position of the fundamental at every value of q, double that relative frequency, and that gives us the value of beta at that value of q. So here I'm showing what that value of beta was for particular q values as we went through that scan. The beta value ranged from a value of 0 at q equals 0 to a beta value of 1 when q equaled 0.908. What that tells us is the ion frequencies, and therefore beta, vary depending where the ion is in the stability diagram. So that implies that beta is a function of q at least, and actually it transpires that it's also a function of A. And it's a pretty complex function. What this equation tells us is that beta squared in either the x or the y direction equals the corresponding A value plus two infinitely long fractions that include values for both q, beta, and A. The little sets of dots at the bottom of each of those two big fractions tells us that those continue infinitely. So this is what's known as an irrational function. You never get to the end of it. And it's also a function you can't actually solve with algebra. Isn't that fun? But it's not a mysterious function that we only see for the motion of ions in quadrupoles. This function for beta is common for all objects undergoing Mathieu-type motion. And with modern computers, this is a function we can easily solve numerically. In order to do this, first of all we've got to truncate the fraction to some manageable length. Perhaps to the level that involves beta plus 24 and beta minus 24. Then we need to fix two of the parameters, so say A and Q. Then we let the computer iterate until it finds a value of beta where the equation is true, so that means the right-hand side equals the left-hand side. Now what do you think happens if we use that approach to find values of beta across the whole of the stability diagram? In order to draw the lines on this stability diagram, I've numerically solved the beta equation to find combinations of A and Q that correspond to specific values of beta. The red lines are solutions for beta in the x direction, and the blue lines are for beta in the y direction. The beta x lines go from 0.1 to 1 in steps of 0.1, and the beta y lines go from 0 to 1 in steps of 0.1. So this confirms what we already expected, that the ion frequencies in both the x and the y direction will vary across the entire stable region. But one interesting feature is that the edges of the stable region correspond to specific values of beta. So the blue boundary corresponds with the beta y equals 0 line, and the red boundary with the beta x equals 1 line. So why is the stable region in the Mathieu stability diagram bounded by these two solutions for beta? So let's consider this ion here, which I'm arbitrarily starting just somewhere in the middle of the stable region. What happens if I now try to move that ion across this beta x equals 1 boundary? As this ion moves towards the boundary, its ion oscillation frequency increases, and at the same time its beta value increases until, as it crosses the boundary, its beta value is exactly 1. If we substitute beta equals 1 into this equation, what this shows us is, at that point, the ion fundamental frequency is exactly half the drive frequency. So at that frequency, the ion's oscillation becomes resonantly excited, and it rapidly gains amplitude until it strikes one of the X rods. So that explains why you can never get an ion to pass this top beta x equals 1 boundary. But what about if we go in the other direction? This time, as we approach the boundary, the ion oscillation frequency decreases, until as it crosses the boundary, its beta in the y direction equals 0. Now, when beta equals 0, the ion fundamental frequency is 0 times the drive frequency, so the ion has a frequency of 0. Now if that ion was ever heading away from the centre of the quadrupole and turned round and came back, That would imply that it had some kind of frequency. It's oscillating and returning on itself. But if an ion has a frequency of 0, that means if it starts moving away from the center of the quadrupole, it will just continue to do so until it hits one of the Y rods. So that's why beta Y equals 0 forms the left-hand edge of the stability region. As ions cross that, their frequency goes to 0, they no longer turn round to go back into the quadrupole, and they just keep continuing moving until they strike the Y rods. And so if we go back to this slide that I showed you in the previous session, that's why I've shown the trajectories the way I have. This green ion is outside the beta x equals 1 boundary, so it's being resonantly excited by the quadrupole drive frequency, and its amplitude of oscillation increases until it hits the rods. Whereas the grey ion is outside the beta y equals 0 boundary, so it has a frequency of 0, and although its amplitude of oscillation doesn't change, its centre of oscillation just keeps drifting out from the centre of the quadrupole until it strikes one of the rods. And that's really the underlying secret explaining why the Mathieu equations calculate values of A and Q for you, and you can tell from those whether the ion trajectory is stable or not. Really what that A and Q is telling you is whether the ion oscillation frequency is somewhere between 0 and exactly half the drive frequency. So that's why the axes of the stability diagram are A and Q, and the curves that form the edges of the stable region are solutions for beta. Now all I've shown you so far is actually a tiny part of the stability diagram. Now let's zoom out and look at a much wider region. So using the same numerical approach I described earlier, here I'm solving the beta x equation for the values where beta equals 0 and beta equals 1. Ions that plot inside that long claw shape will be stable in the x direction. And now if I repeat the process for finding the beta equals 0 and beta equals 1 lines in the y direction, I get an upward pointing claw like this. Ions plotting inside this claw are stable in the y direction. Now of course we're only interested in ions that are stable in both directions, so let's superimpose both stable regions on top of each other. And now we can see there's only a small region where ions are stable in both the x and the y directions at the same time. So let's just zoom in to that region. Ions that plot in this red zone are stable in the x direction, whereas ions that plot in the blue region are stable in the y direction. And ions that are stable in both directions are the ones that we'll see passing all the way through the quadrupole. Now because the Mathieu equations tell us that the Mathieu parameter AX equals minus AY and minus QX equals QY, that means the graph is symmetrical and we only need to consider the positive quadrant. And that's why the quadrupole stability diagram normally looks like this. Now for the quadrupole ion trap, the beta equation remains the same, but now remember that AR equals minus 2 times AZ and QR equals 2 times QZ. So the claws on the stability diagram are no longer the same size. And now, the region of the stability diagram where ions are stable in both the R and the Z direction at the same time is no longer symmetrical. And that's why, for the ion trap, you can't just show the positive quadrant of the stability diagram. Now I just want to begin looking at the quadrupole trapping well depth before we finish this session. As ions oscillate down the length of a quadrupole, or as they're trapped inside an ion trap, there must be some force which is causing that trapping. So we call that the effective trapping potential, or the potential well. The greater that force, or if you'd like to think about it the other way, the deeper the trapping well, the more ions can be trapped. So how can we work out how deep that trapping well is? One measure of the strength of gravity on Earth, that is the depth of our gravitational well, is to keep throwing objects in the air at faster and faster speeds until you find the speed beyond which nothing comes back down again. This is known as the escape velocity. And we can use the same approach to find the trapping well depth in quadrupoles. To do this, we build a model of our quadrupole mass filter or ion trap in an ion trajectory modelling package. Then we create ions at the centre of that trap and fire them outwards with increasing energy until we find the maximum energy we can give ions and yet have them still remain trapped within the quadrupole field. And because in the model we have full control over all the parameters, for example the A and Q value, we can find how this trapping well depth varies across the whole of the stability region. And that's what I'm showing here. You can see the shape of the stability region, and the colour axis shows you the depth of the trapping well at a particular point. So you can see the trapping well depth for ions is deepest right down on the Q-axis at a value of about 0.6. And unsurprisingly, the trapping well depth is 0 in the unstable regions. And this figure is showing the trapping well depth for a quadrupole mass filter. So let's have a look and see what happens if we put a scan line on here. So as you recall, when used as a quadrupole mass filter, the scan line passes through the very tip of the stable region. And up at the tip you can see that the trapping well depth is very much lower than it was down on the Q-axis, where we might be using the quadrupole, for example, in a linear ion trap or as an RF-only ion guide. Now if we were to reduce the resolution of this quadrupole, that would simply mean changing the angle of the scan line so that it passes through a thicker part of the tip of the stability diagram. But you can see that will also involve increasing the trapping well depth that ions see as they pass through that quadrupole. So what effect will this have on the sensitivity? The sensitivity of quadrupoles varies approximately by the square of the trapping well depth. So if you're using a quadrupole mass filter based device and you need more sensitivity, then you can trade off resolution to gain this. But if you go too far in that direction, you'll no longer have the resolution to tell apart different analytes, so it's always a compromise that you've got to consider. Now if we're using a linear quadrupole in RF-only mode, for example as an ion guide or in a 2D ion trap, that means all the ions will be on the Q-axis. Now here I've plotted how the trapping well depth varies as we move along that Q-axis up to the stability boundary. The well depth is deepest about a Q value of 0.6, and it drops to 0 at both the high and low values of Q. Now remember, Q is inversely related to the mass to charge ratio of the ions. So if the well depth varies for different values of Q, that means the well depth also varies for different mass to charge ratios of ions. And this then goes on to have a profound effect on the sensitivity of different ions going through the same quadrupole if they have different mass to charge ratios. So imagine we have coming from our ion source an ion beam containing the signals of 9 different ions, all with identical intensities, and all which happen to be equally spaced in the Q dimension. Now remember that the sensitivity of the quadrupole will vary as a function of its trapping well depth. So that means that after the quadrupole component, the intensities of the ions may not be the same anymore. They may have been restricted by the sensitivity of the quadrupole they passed through. So that may mean you see the most sensitivity for ions that had a Q of 0.6, but much less sensitivity for ions of higher and lower values of Q, like this. Now remember, Q is inversely proportional to the mass to charge ratio, so we can convert this Q value to the underlying mass to charge ratio values. And this biasing effect on the ion intensities is solely a function of the fact that the ion beam has passed through a quadrupole component. So just because in a mass spectrum you see lower intensities of very high mass ions compared to lower mass ions, that may not necessarily solely be because there was actually fewer of those components in the original sample. This may be an artifact of the fact that your ion beam has passed through one or multiple quadrupole components in the instrument before being detected. So there's quite a lot of material in this session, and here are some things that you might want to try to remember. So why are the 3D ion trap equations different from the quadrupole mass filter ones? What's the difference between 3D and 2D ion traps? Can you remember all the different names of 3D and 2D ion traps? Or what the benefit of using a 2D linear ion trap over a 3D quadrupole ion trap is for the same radius? You should remember that the ion oscillation frequency in quadrupole fields depends on where the ion is in the stability diagram, because beta is a function of A and Q. and you should try to remember the relationship between the ion oscillation frequency, the drive frequency, and omega. Ions with an oscillation frequency of 0 will be lost from the trapping well. Can you remember why? And ions with an oscillation frequency exactly half the drive frequency will be ejected from the trapping well. And can you remember why that is as well? And finally, the quadrupole trapping well has a depth that is not constant across the stability region, and this has an effect on the sensitivity. Can you remember what that is? And can you also remember why this might have an effect in the intensities of ions you see in a mass spectrum? Hopefully you'll be able to find the answer to these questions earlier on in the materials for this session. I've also made an HTML5 version of this video. The benefit of watching the presentation in HTML5 mode is that you get to go through it at your own pace and answer questions and problems as you go along to help you understand the material. To find the HTML5 versions, go to the Kilgour Lab website at www.kilgourlab.com and then go to the Teaching Resources page. On there you'll find a whole variety of resources to help you learn about mass spectrometry. I hope you enjoy them. And this brings us to the end of the materials for this second session on quadrupoles and ion traps.